Welcome everyone to our lecture today in robotics. Today we are going to begin a new chapter in our subject, which is manipulator kinematics. So kinematics is considered to be the science of motion that treats the subject without regard to the forces that cause it. So we simply study the geometry of our manipulator without considering the force that cause this geometry in this shape. Once we consider the geometry, we represent in this case the dynamics, but without considering the forces, it will be kinematics. So in kinematics, we study the position, velocity, and the acceleration, and all derivatives of the position variables without considering the forces that causes the manipulator to be in this form. Again, we simply study the geometry of this shape. We can consider the position and all its derivatives. All this occur without considering the forces. This means what we mean by kinematics. In case of dynamics, we consider the forces that causes the change in the position, velocity, and the acceleration. So, for such a manipulator here, in order to deal with the complex geometry, we simply affix the frames of the various parts and describe the relationship between each frame and the other. For example, in this manipulator, this is the base, this is the fixed base. We have here first joint, second joint, third, and fourth joint. So we have here four joints, which represents a 4-degree of freedom system. And we can describe the relationship between each frame and the other, considering a fixed frame, which is the base frame here. So the main topic in this lecture, we compute the position and the orientation of this end effector as seen by this gripper here. We name this part here as the end effector, and what we are going to do is to compute the position and orientation of this end effector relative to this fixed base as a function of all the joint variables. This is the main issue in this chapter. So again, we simply represent or describe the position and the orientation of this end effector frame with respect to the base frame as a function of all the joint variables. The link of the robot is simply, as we mentioned before, the manipulator simply consists of a number of links, and all these links are connected in a chain by a joint. So we have here as shown several types of the joints that connect the links together. Some of the joints are called or have the term lower pair. This term is used to describe the connection between the two links when the relative motion is characterized by a surface sliding over the other. This can be seen here in this type of joint. We have the two links, and we have here a common surface area between the two links. Such a link is such a joint. It can be called a revolute joint. The second one is a prismatic. We can see here two cylinders, and there is a common area between the two surfaces of the cylinders. And this type of link, simply the cylinder is extended away from the other to have a longer length. This one is a cylindrical. It has the same idea as for the prismatic. In this cylindrical joint, simply we have also two surfaces that slides over each other. Here we have a planar joint. There are two planes which are placed over each other. So we have here a common area between this plate and the other. Screw with this thread. We have also two areas that slide over each other. We have this spherical construction. We have here a plate, and with this construction we have a sphere that can be rotated with n degrees of freedom, as we see. Simply, in our manipulator, we will use only the first two types of joints, which is the revolute and the prismatic type of joint. So only these two types, revolute and prismatic, will be considered. Because we will use only 1 degree of freedom in order to easily describe the manipulator system based on the dynamics and the kinematics. So each joint simply represents 1 degree of freedom, and that will be considered in our course here. So only the two types will be used for the simplicity of describing the kinematics and dynamics. For the link description, we have mentioned before, this is the fixed base, and this is the end effector. And in the shown figure, we begin with the numbering from the fixed base till the end effector. So the first link is this link 0, which is fixed. Then comes this joint here, joint 1. This joint is the common joint between link 0 and link 1. Link 1 is connected with link 2 through joint 2, and link 3 is connected with link 2 throughout joint 3. Then link 4 is connected with link 3 throughout the joint 4, which lies between both the two links. And we have here joint 6 with link 6 and link 5 with joint 5. So we have here 6 links with 6 joints. We begin the numbering from the fixed base till reaching the end effector at the end of the chain. In order to position this end effector, Generally, in 3 space, we need a minimum number of 6 joints, as seen in this example. This is because the description of an object in space requires 6 parameters, 3 for the position and 3 for the orientation. So typically manipulators have 5 or 6 joints in order to reach the desired position of this end effector. For the description of the link is simply this rigid body, which describes the relationship between the two neighboring joints. We have here joint on this axis. We call it I-1, and the other joint is simply axis I, and in between is this link I-1, referred to the joint with the lower number I-1. So the link is considered to be a rigid body that defines the relationship between the two joint axes here. So the joint axes are simply these straight lines in space. Joint axis I, which is this one, is defined by this line in space, or a vector direction about which link I rotates relative to link I-1. Link I is not seen in this figure, but can be represented with the link connected to the axis I here, and this link I can be represented relative to link I-1 throughout this axis I. And the distance between both axes is simply the straight line, which is represented by the mutual perpendicular. This straight line is simply perpendicular to the extension of this axis, and at the same time this is the perpendicular with respect to axis I-1. How can I reach this perpendicular line, which is the common line between the two axes? This can be represented. We imagine we have a cylinder. The cylinder around this axis, and we simply increase the radius of the cylinder till the cylinder touches the axis I. At the point of tangency, at which the surface of the cylinder touches axis I, this radius is simply the perpendicular line AI-1 between axis I-1 and axis I. So once again, we describe such link with respect to the neighbor axis. So link I-1 is represented with axis I-1 and axis I. The two joints can be represented with two straight lines in space. Joint axis I is defined by a line in space or a vector direction about which link I rotates relative to link I1. The distance along this line is simply the mutual perpendicular between axis I-1 and axis I. Is the link length. The link length is simply this common perpendicular line between axis I-1 and axis I. expression is called the link twist. We simply twist this link by changing the angle of the joint with respect to the other joint on the other end, and we simply imagine a plane, which is this plane here, whose normal is the mutual perpendicular line we have just constructed. We imagine this plane, and the normal is the mutually perpendicular line, and we can project the axis I minus 1 and I onto this plane. So the projection of this line is simply this dash line, and we measure the angle between them, which is the angle between the axis I minus 1 to the axis parallel to the axis I. So this dash line simply represents axis I, which is parallel to it, and we measure the angle alpha I minus 1, which is the angle between the axis I minus 1 and axis I represented in this dash line. This can be measured in the right hand sense as we have seen. So the kinematic function of such a link is to maintain a fixed relationship between the two joints it supports. This relationship can be described with the two parameters, the link length A and the link twist alpha. So each link in our manipulation, in our manipulator chain, we can be described only with these two parameters. First is the length, which represented by the perpendicular line between the two straight line of the axis, and secondly is the link twist, which is the angle between this perpendicular line and the plane representing which is the plane and the plane whose normal is the mutual perpendicular line. So in this description we have alpha I minus 1, which is the angle between axis I minus 1 and axis I. The lines with the triple hash are parallel, which is this line and this line. In some cases, such lines, which is the line of axis I minus 1 and axis I, can be represented with intersecting axes. In this case, it is free to assign the sign of the angle alpha minus 1, either in this direction or on the opposite direction. Let's have an example on how to describe the relationship between the two axes for such a link as shown in figure. This is the geometrical view of a given link. The bearing A represents the lower number joint, which is represented on the previous figure as AI minus 1. and bearing B, which is AI. The length between is 5 inches, and his diameter of, and this is the width of the bearing is 2 inch, and here is 2 inch, and we have a twist angle between them as shown in this view is 45 degrees. What we need here is to find the description of this link. The description is to simply get the length between the two joints and to find the twist of this link according to the geometry of the shape. These holes are centered in each bearing, so by inspection, the common perpendicular line, according to this view here, we get the center line of the hole of bearing A, which is this hole here, the center line which passes through this hole, and the center line through this hole, and get the intersection. The intersection will be accurately at this point where the pointer is fixed here, because this is the intersection between the center lines of bearing A and bearing B. So at this point, we can see it lies right down the middle of the bar in between. We try to move in this direction, so the center point simply lies not at the center of the bar, but simply somehow low, a little bit lower, which is right down the middle of the bar here. So simply the link length is the whole length passing through this point on the bar, which is measured from here, this center line to this center line. Simply divide the width of this block of bearing A on 2. So we have here 5 inch plus 1 inch on this side and 1 inch on the other side of bearing B. So the total length is 5 plus 1 plus 1. The total length will be 7 inches, which is the length of the link. And on the end view, we actually show the projection of the bearing onto the plane whose normal is the mutual perpendicular. What does that mean? The mutual perpendicular is simply this line which passes through the right down the middle of the metal bar, and we simply draw the extension of one of the link of the joints, and we measure the link twist by the previous method by having the line parallel to the line in order to form the plane whose normal is the mutual perpendicular. So in this case, the mutual perpendicular is the angle measured between the mutual perpendicular and the extension of the line of the other joint, which is in this case, using the right hand sense, is 45 degrees, because the twist here is 45. So in this case, the normal perpendicular forming the plane will, after projecting the extension of the bearing, we measure the angle between the extension and the plane. It will be, in this case, 45 degrees. By this simple way, we can describe any link in our manipulator chain, which can be described throughout only two parameters, which are the link length and the link twist. Link length is measured throughout the common perpendicular, and link twist is measured throughout the angle between the plane, whose normal is the mutual perpendicular, and the extension of one of the bearing to the other. So I am now at the end. Thank you very much for your attention.